So here's something that might seem a little strange to think about as you're lying there, getting comfortable, letting the day wind down. Right now, at this very moment, time is not passing at the same rate for every part of your body. The clock for your head is ticking just a tiny, tiny bit faster than the clock for your feet. The difference is absurdly small. We're talking nanoseconds over an entire lifetime. But it's real. It's not a metaphor. It's not a thought experiment. It's a measured, verified, physical fact about the universe you're lying in right now. And honestly, when you sit with that idea for a moment, really let it settle, it's one of the most beautifully strange things about being alive in this particular cosmos. Time dilation. You've probably heard the phrase before. Maybe in a physics class, maybe in a movie, maybe someone mentioned it at a party, and you nodded along and thought, yeah, I sort of get that. Something about clocks running slow near black holes, or astronauts aging differently, or twins. There's always something about twins. And the thing is, most people have this vague sense that time dilation is real, that Einstein figured it out, and that it has something to do with going really fast or being near something really heavy. But the actual mechanics of it, the why and the how, the way it connects to your everyday life in ways you've never noticed, that's where it gets genuinely fascinating. And that's what we're going to talk about tonight. Slowly, gently, no rush at all. Let's start at the beginning. Not the beginning of time dilation as a concept. We'll get there. But the beginning of the problem. The thing that was bugging physicists in the late 1800s that eventually led a 26-year-old patent clerk in Switzerland to rethink the entire nature of reality. The problem was light. By the mid-19th century, physicists had gotten remarkably good at understanding waves. Sound waves, water waves, waves on a string. They had elegant mathematics for all of it. And then, James Clerk Maxwell, working in the 1860s, pulled off one of the great unifications in the history of science. He showed that electricity and magnetism weren't separate things at all. They were two faces of the same phenomenon, and when you wrote down the equations that described them together, something extraordinary fell out of the math. A wave, an electromagnetic wave. And when Maxwell calculated the speed of that wave, it came out to about 300,000 kilometers per second, which was, to everyone's astonishment, the known speed of light. Light wasn't just some mysterious luminous substance. It was an electromagnetic wave. That was a staggering insight. But here's the thing. Every other wave physicists knew about traveled through a medium. Sound travels through air. Ocean waves travel through water. Vibrations travel through a guitar string. So naturally, the question became, what medium does light travel through? What's the stuff that's vibrating when a light wave passes by? And they gave this hypothetical stuff a name, the luminiferous ether. This invisible, weightless, perfectly transparent substance that supposedly filled all of space, permeated everything, and served as the canvas on which light painted its waves. Now, if the ether existed, it had some interesting implications. Think about it this way. If you're standing still and you clap your hands, the sound wave moves away from you at the speed of sound, about 343 meters per second in air. But if you're running forward and you clap, the sound wave still moves through the air at 343 meters per second relative to the air. Relative to you, though, the sound moving in the direction you're running is effectively a little slower because you're chasing it, and the sound moving behind you is effectively a little faster because you're running away from it. The medium, the air, sets the speed. Your motion through the medium changes what you measure. So if light worked the same way, if it traveled through the ether at 300,000 kilometers per second, then the Earth's motion through the ether should affect the measured speed of light. The Earth is orbiting the Sun at about 30 kilometers per second. That's not nothing. If you measured the speed of light in the direction the Earth was moving, it should seem a tiny bit slower. If you measured it in the perpendicular direction, it should seem a tiny bit different. The difference would be small, but it should be detectable with sufficiently precise instruments. And that brings us to one of the most famous experiments in the history of physics. Albert Michelson and Edward Morley, working in Cleveland, Ohio, in 1887. Michelson was a fascinating character, a German-born American physicist who was absolutely obsessed with measuring the speed of light. He'd been working on it for years. He'd designed an instrument called an interferometer, which was ingeniously clever. Here's how it worked. You take a beam of light and you split it in two using a half-silvered mirror. One beam goes off in one direction, bounces off a mirror, and comes back. The other beam goes off at a right angle, bounces off its own mirror, and comes back. Then the two beams recombine. Now, if the two beams traveled exactly the same distance in exactly the same time, they'd arrive back perfectly in sync. Their wave peaks would line up. But if one beam took even a tiny bit longer than the other, the waves would be slightly out of step, and you'd see interference fringes, a pattern of light and dark bands. By watching how those fringes shifted, you could detect incredibly small differences in the travel time of the two beams. The idea was straightforward. Point one arm of the interferometer in the direction the Earth is moving through the ether, and point the other arm perpendicular to it. The beam going with and against the ether wind should take a slightly different amount of time than the beam going across the ether wind. Rotate the whole apparatus, and the fringe pattern should shift. Michelson and Morley went to extraordinary lengths to make this work. They mounted the interferometer on a massive sandstone slab, floated the whole thing on a pool of mercury to eliminate vibrations and allow smooth rotation, and set up in a basement to minimize temperature fluctuations. The precision was remarkable for the era, and the result? Nothing. No shift. No fringe movement. No sign whatsoever that the Earth was moving through any ether. The speed of light appeared to be exactly the same in every direction, regardless of how the Earth was moving. This was deeply, deeply confusing. It wasn't just a null result. It was a null result that seemed to contradict basic physics. If light was a wave in a medium, and the Earth was moving through that medium, there had to be a difference. But there wasn't. Now, physicists didn't just throw up their hands. Several very smart people tried to rescue the ether. The most notable was Hendrik Lorentz, a Dutch physicist who, along with George Fitzgerald, an Irish physicist, proposed something remarkable. What if, they suggested, objects moving through the ether actually physically contract in the direction of motion? What if the arm of the interferometer pointing in the direction of Earth's motion was getting slightly shorter, just enough to compensate for the time difference? It sounds like a wild ad hoc fix, and in some ways it was, but Lorentz worked out the mathematics rigorously. He derived a set of transformation equations, the Lorentz transformations, that described exactly how lengths would contract and how time would dilate for objects moving through the ether. These equations were mathematically beautiful, and they perfectly explained the Michelson-Morley result. But here's what's really interesting. Lorentz still thought the ether was real. He thought these contractions were physical effects caused by motion through the ether. The ether was still the foundation. The contractions were a mechanical consequence of moving through it. It took someone else to look at those same equations and see something completely different. Someone who was willing to throw away the ether entirely and ask, what if the speed of light isn't just measured to be the same in every direction? What if it actually is the same in every direction, for every observer, no matter how they're moving? What would that mean for our understanding of space and time? That someone, of course, was Albert Einstein, and the year was 1905. Now, Einstein in 1905 wasn't a professor. He wasn't at a prestigious university. He was working as a technical expert, third class, at the Swiss Patent Office in Bern. He was 26 years old. He'd struggled to find an academic position after finishing his degree at the Polytechnic in Zurich. His professors hadn't been particularly impressed with him. He'd been good at physics, but had a habit of skipping lectures and teaching himself from the latest papers and books, which didn't endear him to the faculty. One professor, Heinrich Weber, reportedly told Einstein that he was a smart boy, but had a big failing. He wouldn't let anyone tell him anything. But the patent office job, tedious as it might sound, actually gave Einstein something valuable. Time to think. He'd finish his patent evaluations efficiently, and then he'd work on physics. He had a small circle of friends in Bern, Michel Bessot, Conrad Habicht, Maurice Solavine, and they'd meet regularly to discuss physics, philosophy, and mathematics. They called themselves the Olympia Academy, which was a cheeky name for three guys sitting in an apartment eating sausage and arguing about Ernst Mach and David Hume. And it was Mach and Hume, actually, who influenced Einstein's thinking in a crucial way. Both philosophers were deeply skeptical of concepts that couldn't be directly observed or measured. Mach, in particular, had argued that the concept of absolute space, the idea that there's a fixed, universal stage on which everything happens, was metaphysical nonsense. You can't observe absolute space. You can only observe the relative motion of objects with respect to each other. This idea lodged in Einstein's mind and wouldn't let go. So when Einstein sat down to think about the problem of light, he approached it differently than Lorentz had. He didn't ask, how can we modify our physics to explain why we can't detect the ether? He asked something more radical. What if there is no ether? What if the speed of light is simply a fundamental constant of nature, the same for all observers, regardless of their motion? That's one of the two postulates of special relativity. The first postulate is the principle of relativity itself. The laws of physics are the same in all inertial reference frames. An inertial reference frame is just a fancy way of saying a point of view that isn't accelerating. If you're sitting on a train, moving at a perfectly constant speed on perfectly smooth tracks, with the curtains drawn, there's no experiment you can do inside that train to determine whether you're moving or sitting still. The physics is the same. This wasn't new. Galileo had articulated this idea centuries earlier. Newton's mechanics obeyed it. The second postulate was the revolutionary one. The speed of light in a vacuum is the same for all inertial observers, regardless of the motion of the light source or the observer. This sounds innocuous, but think about what it means. If I'm standing still and I shine a flashlight, the light moves away from me at 300,000 kilometers per second. Now, if you're flying past me at half the speed of light and I shine that same flashlight, you'd expect, based on everyday intuition, that you'd measure the light moving at only 150,000 kilometers per second relative to you because you're chasing it. But no, you measure it at 300,000 kilometers per second, the full speed, always. That breaks everything you think you know about how velocities add up. If you're on a train going 100 kilometers per hour and you throw a ball forward at 50 kilometers per hour, someone standing on the platform sees the ball going 150 kilometers per hour. Velocities add. But light doesn't play by those rules. Light always goes at the same speed, no matter what. And here's where Einstein's genius really shows. He didn't flinch from the implications. If the speed of light is truly constant for all observers, then something else has to give. And what gives, what has to give, is our intuitive understanding of space and time. They're not fixed. They're not absolute. They're flexible. They stretch and compress depending on how you're moving relative to someone else. That's time dilation, right there. It falls directly out of those two postulates, and you don't even need complicated math to see why. Let me show you. Imagine you're on a spaceship, a nice, smooth-riding spaceship, no turbulence, constant velocity, and you've got a simple clock. This clock works by bouncing a pulse of light between two mirrors, one on the floor and one on the ceiling. The light goes up, hits the top mirror, bounces back down, hits the bottom mirror. That's one tick. Up and down, up and down. It's the simplest clock you can imagine, and it runs on light, which makes it perfect for this thought experiment. Now, from your perspective, inside the ship, the light is going straight up and straight down. The distance it travels each tick is just twice the distance between the mirrors. Simple. But now imagine I'm floating outside the ship, watching you fly past me at tremendous speed. What do I see? I see the light pulse go up, but while it's traveling upward, the ship has moved forward. So from my perspective, the light doesn't go straight up. It goes diagonally, and then it comes back down diagonally. The light traces a zigzag path. And here's the crucial part. That diagonal path is longer than the straight up and down path you see inside the ship. The light has to cover more distance from my point of view. But, and this is where the second postulate kicks in, the speed of light is the same for both of us. I measure it at 300,000 kilometers per second. You measure it at 300,000 kilometers per second. Same speed. But from my perspective, the light has to travel a longer path. Same speed, longer distance. That means it takes more time. Your clock, as I watch it from outside, is ticking slower than mine. Your time is running slower than mine, not because your clock is broken, not because of some mechanical effect. Time itself, the actual passage of moments, is slower for you relative to me. And the faster you're going, the more pronounced this effect becomes. At everyday speeds, driving a car, flying in a plane, the effect is so tiny, it's essentially unmeasurable without atomic clocks. But as you approach the speed of light, the effect becomes dramatic. At 87% of the speed of light, your clock runs at half speed compared to mine. At 99%, your clock is ticking about 7 times slower. And at the speed of light itself, well, time stops entirely, which is one of the reasons nothing with mass can actually reach the speed of light, but we'll come back to that. This is special relativity. Published by Einstein in June 1905 in a paper with the unassuming title, On the Electrodynamics of Moving Bodies. No footnotes. Almost no references to other physicists' work. Just pure thought, laid out with startling clarity. And buried in that paper, in the implications of those two simple postulates, was a complete overhaul of humanity's understanding of time and space. Newton had given us a universe with a single universal clock, absolute time, ticking at the same rate everywhere, for everyone, always. Einstein replaced it with something far stranger and far more beautiful, a universe where time is personal, where your experience of duration depends on how you're moving through space, where simultaneity itself, the idea that two events happen at the same time, becomes a matter of perspective. And the wildest part? This was only half the story, because special relativity deals with constant velocities, steady, straight-line motion. It doesn't say anything about gravity. And gravity, as it turns out, does something to time that's even more surprising. Something that connects directly to that fact I mentioned at the very beginning, about the clocks in your head and your feet ticking at different rates. That's not special relativity. That's general relativity. And to get there, Einstein had to go on a journey that would take him another 10 years, push him to the absolute limits of his mathematical ability, and lead him to what many physicists consider the most beautiful theory ever written. But the road to general relativity started with a deceptively simple question, the kind of question that most people would hear and think, well, that's obvious. Why are you even asking that? The question was this: why does a heavy object and a light object fall at the same rate? And Einstein later said that the thought which led him to the answer was the happiest thought of his entire life. That's a remarkable thing to say, isn't it? Not his wedding day, not the birth of his sons, not even the moment he realized special relativity was correct. No, the happiest thought of his entire life was about falling. Specifically, it was about what it would feel like to fall freely, to be in a state of pure gravitational free fall, and what that experience would tell you about the nature of gravity itself. The year was 1907, just 2 years after special relativity. Einstein was still at the patent office in Bern, though by now he was gaining recognition. He'd been asked to write a review article about his relativity work, and in the process of writing it, he started thinking about how gravity might fit into the picture. And that's when the thought hit him. He later described it vividly. He imagined a person falling from the roof of a house, and he realized that during the fall, that person would not feel their own weight. Think about that for a second. If you're in an elevator and the cable snaps, and let's set aside the terror for a moment and just think about the physics. During those seconds of free fall, you'd float. Your feet would lift off the floor. If you let go of your keys, they wouldn't drop to the ground. They'd hover right next to your hand. Everything in that elevator is falling together at the same rate. And so from your perspective, inside that box, gravity has effectively vanished. You couldn't do any experiment inside that sealed elevator to prove that gravity was pulling you downward. It would feel exactly like floating in deep space, far from any planet or star. And here's where Einstein's genius shows itself again, because he didn't just notice this as a curiosity. He elevated it to a principle. He said, if free fall is indistinguishable from the absence of gravity, then maybe they're the same thing. Maybe what we call gravity isn't a force pulling you down. Maybe it's something about the structure of space and time itself, and what we experience as gravitational pull is really just the natural motion of objects through a curved space-time. This idea became known as the equivalence principle, and it works in both directions. Not only is free fall indistinguishable from zero gravity, but standing on the surface of the Earth, feeling your weight pressing into your feet, is indistinguishable from being in a rocket ship accelerating upward at the same rate. If you were in a windowless rocket accelerating at 9.8 meters per second squared, you'd feel exactly the same as you do right now, sitting or lying wherever you are. You couldn't tell the difference. No experiment you could perform inside that sealed room would reveal whether you were in a gravitational field or accelerating through empty space. Now, you might be thinking, okay, that's a neat observation, but so what? Here's the thing. This equivalence between gravity and acceleration unlocked everything. Because Einstein already knew from special relativity that motion affects time. He'd shown that clocks moving at high speed tick slower. And if acceleration and gravity are truly equivalent, truly, fundamentally, physically the same thing, then gravity must also affect time. That's the logical chain. Acceleration affects time. Gravity is equivalent to acceleration. Therefore, gravity affects time. And that brings us right back to where we started this whole journey, with the clocks in your head ticking at a slightly different rate than the clocks in your feet. Your head is farther from the center of the Earth. It experiences very slightly less gravitational pull. And because of that, time passes very slightly faster up there than it does down at your feet. The difference is absurdly tiny. We're talking about gaining maybe 90 billionths of a second over an entire human lifetime between the top of your head and the soles of your feet. But it's real. It's been measured. And the fact that it's real is one of the most extraordinary confirmations of Einstein's thinking. But let's not jump ahead to the measurements just yet. Let's stay with Einstein in 1907 for a moment, because he's just had this beautiful insight, and now he has a massive problem. He knows what he wants to say, that gravity is geometry, that mass and energy curve the fabric of space-time, and that objects move along the straightest possible paths through that curved geometry. He can feel the shape of the theory, but he doesn't have the math. And this is where the story gets really human, really messy, and honestly, kind of painful. Einstein spent the next 8 years, from 1907 to 1915, struggling to find the right mathematical language for general relativity. 8 years. And these weren't 8 years of steady progress. They were 8 years of wrong turns, false starts, abandoned equations, and moments of genuine despair. He needed a kind of mathematics that could describe curved spaces in 4 dimensions, 3 of space and 1 of time. And he needed equations that would tell you exactly how matter and energy determine that curvature. The math he needed was called Riemannian geometry, and later tensor calculus, and Einstein was not naturally fluent in it. He was a physicist, not a mathematician. His strength had always been physical intuition, thought experiments, seeing the deep structure of a problem before anyone else. The formal mathematical machinery was something he had to learn, and it didn't come easily. He turned to his old friend, Marcel Grossmann, a mathematician he'd known since their student days at the ETH in Zurich. Grossmann was the one who'd helped Einstein get through his math courses back in college. Einstein had famously skipped lectures and borrowed Grossmann's notes to pass exams. And now, years later, Einstein came to Grossmann again and essentially said, "I need help. I have this physical theory, and I need the mathematical tools to express it." Grossmann introduced him to the work of Bernhard Riemann, Gregorio Ricci Curbastro, and Tullio Levi-Civita, the mathematicians who had developed the tensor calculus that would become the language of general relativity. Together, Einstein and Grossmann published a preliminary version of the theory in 1913, called the Entwerf theory. But it wasn't right. Einstein knew it wasn't right. The equations weren't fully covariant, meaning they didn't hold their form in all coordinate systems, which was supposed to be the whole point. The theory was supposed to look the same, no matter how you described your patch of space-time, and these equations didn't quite manage that. So he kept working. And here's where the pressure really mounted, because Einstein wasn't the only one chasing this prize. David Hilbert, one of the greatest mathematicians of the 20th century, had become interested in the problem too. Hilbert was based in Göttingen, Germany, and he had the mathematical firepower that Einstein lacked. In the fall of 1915, both men were racing toward the correct field equations, the equations that would describe exactly how matter curves space-time. Einstein gave a series of 4 lectures at the Prussian Academy of Sciences in Berlin during November 1915, each one refining his equations, each one getting closer. The third lecture, on November 18th, contained a stunning result. Einstein used his nearly complete equations to calculate the orbit of Mercury, and he got the right answer. For decades, astronomers had known that Mercury's orbit had a slight anomaly. Its perihelion, the point of closest approach to the Sun, precessed by about 43 arc-seconds per century, more than Newtonian gravity could explain. People had even proposed a hidden planet, called Vulcan, to account for it. Einstein's equations explained those 43 arc-seconds perfectly, with no fudge factors, no hidden planets, nothing. He later told a colleague that when he saw the result, his heart palpitated. He was so excited he couldn't work for days. And then, on November 25, 1915, he presented the final, correct field equations, what we now call the Einstein field equations. They're often written in a deceptively compact form, capital G, with subscripts mu and nu equals 8pi capital G over c to the 4th, times capital T with the same subscripts. That's it. That little equation relates the geometry of space-time on the left side to the distribution of matter and energy on the right side. John Wheeler, the great American physicist, later summarized it beautifully. Space-time tells matter how to move, and matter tells space-time how to curve. That's general relativity in one sentence. But what does this actually mean for time? Let's bring it back to something you can feel. Imagine you're standing on the surface of the Earth. The Earth's mass is curving the space-time around it, and one of the consequences of that curvature is that time runs slower closer to the source of gravity. Not because there's some force slowing down your clocks. The clocks are working perfectly fine. It's that the space-time itself, the fabric in which those clocks exist, is stretched differently at different distances from the Earth. A clock on the ground floor of a building runs ever so slightly slower than a clock on the top floor. A clock at sea level runs slower than a clock on a mountaintop. A clock on the surface of the Earth runs slower than a clock aboard a GPS satellite orbiting 20,000 kilometers overhead. And that GPS example is where this stops being abstract physics and starts being something that affects your daily life in a very concrete way. Because the GPS system, the network of satellites that tells your phone where you are, depends on extraordinarily precise timing. Each satellite carries an atomic clock, and your position is calculated by comparing the signals from multiple satellites and measuring the tiny differences in arrival time. If those clocks weren't corrected for relativistic effects, the system would accumulate errors of about 10 kilometers per day. Your navigation app would be useless within hours. So every GPS satellite has its clock rate adjusted before launch to compensate for 2 relativistic effects simultaneously. First, special relativity. The satellites are moving at about 14,000 kilometers per hour relative to the ground, so their clocks tick slightly slower due to velocity-based time dilation by about 7 microseconds per day. Second, general relativity. The satellites are higher up in Earth's gravitational field, so their clocks tick slightly faster due to weaker gravitational time dilation by about 45 microseconds per day. The two effects work in opposite directions, and the gravitational effect wins. There's a net gain of about 38 microseconds per day that has to be corrected for. 38 millionths of a second. That's the margin. And if you don't account for it, the whole system falls apart. So here's something worth sitting with for a moment. Every time you open a map on your phone and that little blue dot shows you exactly where you are, that's Einstein. That's the equivalence principle, the field equations, the curvature of space-time, all of it working quietly in the background, correcting the clocks on satellites so that your position is accurate to within a few meters. A theory born from a man imagining what it would feel like to fall off a roof, refined through 8 years of mathematical struggle, validated by the orbit of Mercury, and now embedded in the infrastructure of everyday life. It's one of those things that, once you know it, changes how you see the world just a little bit. But we've been talking about gravity as though it's a smooth, gentle thing, the kind of subtle curvature that makes your head age a few nanoseconds faster than your feet over a lifetime. And for most of our experience, that's exactly what it is. Earth's gravity is relatively weak as these things go. But what happens when gravity gets really strong? What happens when you take Einstein's equations and push them to extremes, to the surface of a neutron star, or worse, to the edge of a black hole? Because that's where time dilation stops being a subtle correction and starts becoming something genuinely strange, something that bends your intuition until it almost breaks. So let's go there. Let's talk about what happens when gravity isn't the gentle pull you feel standing in your kitchen, but something so intense that the fabric of space-time itself gets twisted into shapes that are hard to even describe in words. Start with neutron stars because they're a good stepping stone. A neutron star is what you get when a massive star, something maybe 8 or 10 times the mass of our sun, runs out of fuel and collapses. The outer layers blow off in a supernova, but the core just keeps falling inward, crushed by its own gravity until the atoms themselves can't hold their shape anymore. Electrons get forced into protons, everything becomes neutrons, and you end up with an object that has roughly the mass of our entire sun packed into a sphere about 20 kilometers across. 20 kilometers. That's roughly the size of a city. Imagine taking everything in the sun, all that mass, all that matter, and squeezing it down until it would fit inside Manhattan. The density is almost incomprehensible. A teaspoon of neutron star material would weigh something like 1 billion tons on Earth. And on the surface of that object, gravity is about 200 billion times stronger than what you feel standing on Earth right now. 200 billion times. So what does that do to time? Well, think back to what we said about clocks on GPS satellites. Earth's gravity causes clocks at the surface to run about 45 microseconds per day slower than clocks far away in weaker gravity. That's with Earth's relatively modest gravitational field. On a neutron star, the effect is enormously amplified. A clock sitting on the surface of a typical neutron star would run roughly 20 to 30% slower than a clock far away in flat spacetime. Not microseconds per day. We're talking about a fundamental, noticeable fraction of time itself being eaten by gravity. If you could somehow survive on the surface and look up at the distant universe, you'd see everything out there happening faster. Stars would appear to age more quickly. Events that take a year out in flat space might seem to fly by in what feels like 9 or 10 months to you. The universe would be on fast forward, and you'd be the one running slow. Now here's where it gets really interesting, and honestly, a little unsettling. Neutron stars are extreme, but they're not the most extreme thing Einstein's equations predict. Because there's a limit. If you keep adding mass, keep increasing the gravitational field, at some point, the escape velocity from the surface reaches the speed of light. And once that happens, nothing, not light, not information, not anything, can get out. You've made a black hole. The idea of an object so massive that light can't escape actually predates Einstein by more than a century. John Michell, an English clergyman and natural philosopher, speculated about what he called dark stars back in 1783. Pierre-Simon Laplace had a similar idea a few years later. But those were Newtonian arguments about particles of light being pulled back by gravity, and they didn't really capture what's going on. It took general relativity to show what a black hole actually is, not just a really heavy object, but a region where space-time itself is so warped that all paths, even the path of light, curve back inward. There's no direction you can point that leads away. Every direction is down. The key mathematical solution came remarkably quickly after Einstein published his field equations. Karl Schwarzschild, a German physicist and astronomer, found the first exact solution to Einstein's equations in December 1915, literally within weeks of the final publication. And here's the poignant part of that story. Schwarzschild wasn't sitting in a comfortable university office when he did this work. He was serving on the Eastern Front in World War I, stationed in Russia, calculating artillery trajectories for the German army. In between his military duties, he worked out the mathematics of how space-time curves around a perfectly spherical, non-rotating mass. He sent the solution to Einstein in a letter. Einstein was reportedly amazed that an exact solution could be found so quickly, and he presented Schwarzschild's work to the Prussian Academy in January 1916. Schwarzschild himself never saw the full impact of his discovery. He developed a rare autoimmune disease, pemphigus, while on the front, and he died in May 1916 at the age of 42. One of the most important solutions in the history of physics, worked out in a war zone by a man who had months to live. What Schwarzschild's solution describes is a boundary around a concentrated mass, a spherical surface, at a specific radius where something extraordinary happens to space-time. That boundary is now called the Schwarzschild radius, or the event horizon. For our sun, if you could somehow crush all its mass into a small enough volume, the Schwarzschild radius would be about 3 kilometers. For Earth, it would be roughly 9 millimeters, smaller than a marble. These objects aren't actually black holes because their mass isn't concentrated enough, but the math tells you what the critical radius would be. And here's what's wild about the event horizon when it comes to time. As you approach it, as you fall toward a black hole and get closer and closer to that boundary, gravitational time dilation increases without limit. Not 20%, not 50%. It approaches infinity. To a distant observer watching you fall in, your clock appears to slow down more and more dramatically the closer you get to the horizon. Your movements seem to become sluggish. Light coming from you gets stretched to longer and longer wavelengths, redshifted, losing energy as it climbs out of the gravitational well. You appear to fade, to redden, to freeze. From the outside, it looks like you never quite reach the event horizon. You just get asymptotically closer and dimmer and slower until you fade from view entirely. But, and this is the part that really twists your mind, from your own perspective, falling in, nothing special happens at the horizon. You don't feel a boundary. You don't hit a wall. If the black hole is large enough, you might not even notice anything unusual at the moment you cross the event horizon. Your local experience of time continues perfectly normally. Your watch keeps ticking. Your heart keeps beating. You just can't send any signals back out. You've crossed a one-way boundary in space-time, and from the universe's perspective, you've essentially vanished. Think about what that means. Two observers, one falling in, one watching from far away, have completely irreconcilable descriptions of what happened. The distant observer says you never crossed the horizon, you just faded away. The falling observer says they crossed it just fine and kept going, and both descriptions are, in their own reference frames, correct. This isn't a paradox exactly. It's more a consequence of the fact that time itself is doing different things in different places. There is no single universal clock that everyone agrees on. That idea we started with, way back at the beginning, about time being this absolute river flowing at the same rate everywhere, it's not just slightly wrong. Near a black hole, it's spectacularly, dramatically, almost absurdly wrong. Now, Einstein himself was actually uncomfortable with black holes. He didn't like the singularity at the center, the point of infinite density that Schwarzschild's math seemed to predict. In 1939, Einstein published a paper arguing that black holes couldn't actually form in nature, that matter couldn't be compressed enough for the Schwarzschild radius to become relevant. He thought some physical process would always intervene to prevent collapse. And that was a reasonable position at the time. The nuclear physics wasn't well enough understood to say definitively what would happen to a massive star at the end of its life. But in that same year, 1939, Robert Oppenheimer and his student Hartland Snyder published a paper showing that a sufficiently massive star, once it exhausts its nuclear fuel, has no known force that can halt its gravitational collapse. It just keeps falling inward. They worked through the general relativistic calculation and showed that, from the perspective of a distant observer, the surface of the collapsing star would approach the Schwarzschild radius and appear to freeze there. But from the perspective of someone riding the surface, the collapse would continue right through the horizon in finite time. It was the first rigorous demonstration that black holes are a genuine prediction of general relativity, not just a mathematical curiosity. And then, of course, Oppenheimer got a little busy with other things. The Manhattan Project consumed his attention for the next several years, and the physics community largely set black holes aside. It wasn't until the 1960s that the subject really came roaring back, driven by new mathematical tools and, crucially, by new astronomical observations that suggested these objects might actually exist out there in the universe. The term black hole itself didn't even exist until 1967, when the physicist John Wheeler, the same Wheeler who gave us that beautiful summary about space-time telling matter how to move, coined it during a lecture. Before that, people called them frozen stars, or collapsed stars, or various other clunky names. Wheeler had a gift for language, for finding the phrase that captures the imagination, and black hole stuck immediately. It's one of those rare cases where the name itself helped drive interest in the science. But let's come back to time, because there's a specific scenario that makes gravitational time dilation near a black hole feel visceral rather than abstract. Imagine two people. One stays in a stable orbit far from a black hole, far enough that the gravitational time dilation is negligible. The other one takes a trip. They descend in a spacecraft toward the black hole, skim close to the event horizon. Not crossing it, just getting very close, and then fire their engines and climb back out to rejoin their friend. What happens? The person who went close to the black hole has aged less, potentially much, much less. Depending on how close they got and how long they spent there, the difference could be enormous. Their friend who stayed far away might have aged decades, while the traveler aged only hours. This is gravitational time, dilation taken to its extreme. It's essentially time travel into the future. You're not breaking any laws of physics. You're not doing anything exotic or hypothetical. You're just exploiting the fact that time runs slower in stronger gravitational fields, and near a black hole, the field is strong enough to make the effect staggeringly large. If this sounds familiar, it might be because you've seen it dramatized. The movie Interstellar, directed by Christopher Nolan, used exactly this scenario. The characters visit a planet orbiting close to a massive black hole called Gargantua, and for every hour they spend on that planet, 7 years pass for their colleague waiting in orbit farther away. The science consultant for that film was Kip Thorne, a theoretical physicist who spent decades working on general relativity and black hole physics, and who later won the Nobel Prize in 2017 for his role in the detection of gravitational waves. Thorne insisted that the film's depictions be consistent with Einstein's equations, and that time dilation scene, as emotionally devastating as it is in the movie, is grounded in real physics. The numbers are pushed to dramatic extremes, but the underlying mechanism is exactly what Einstein's field equations predict. And this brings us to something that I think is genuinely profound, something worth letting settle in your mind as you lie there. Time dilation isn't just a quirky prediction of a theory. It's a measured, confirmed, engineered around feature of the universe we actually live in. We've seen it with muons in cosmic rays. We correct for it in GPS satellites. We've measured it with atomic clocks flown on airplanes and placed at different altitudes. And the same equations that describe those tiny, everyday effects also predict the extreme warping of time near neutron stars and black holes. It's all one continuous phenomenon, just dialed up or down, depending on how strong the gravity is or how fast you're moving. So we've talked about gravity bending time, and we've talked about velocity bending time, and we've pushed both to their extremes. But there's another thread here that we haven't fully pulled on yet. The experimental thread. Because it's one thing to say Einstein's equations predict all of this. It's another thing entirely to actually go out and measure it, to build instruments precise enough to detect differences of billionths of a second, and to show that the universe really does behave this way. And the story of how people actually tested time dilation, the experiments, the clever tricks, the arguments, the moments when the data came in and everyone in the room just stared at the numbers and realized the universe had just told them something extraordinary. That story is one of my favorite threads in all of physics. So, let's pull on it. The first real experimental confirmation of time dilation didn't come from clocks or satellites or anything you might expect. It came from particles, tiny, subatomic particles raining down on us from space. And the story starts with cosmic rays. So here's the setup. High-energy particles, mostly protons, come screaming in from deep space at nearly the speed of light. When they slam into the upper atmosphere, maybe 80 or 100 kilometers up, they collide with nitrogen and oxygen molecules and produce a shower of secondary particles. One of the most common particles in that shower is something called a muon. Now, a muon is basically a heavier cousin of the electron. It has the same charge, behaves similarly in a lot of ways, but it's about 207 times more massive. And here's the key thing about muons. They're unstable. They decay. A muon sitting still in a laboratory has an average lifetime of about 2.2 microseconds. That's 2.2 millionths of a second. Blink and you've missed about 100,000 muon lifetimes. So think about what that means. These muons are created way up in the atmosphere, let's say 15 kilometers up. Even if they're traveling at the speed of light, which is the absolute fastest anything can go, in 2.2 microseconds, light only covers about 660 meters. So a muon born at the top of the atmosphere should only be able to travel about 660 meters before it decays, even at the speed of light. It should never reach the ground. It should decay long before it gets anywhere close to us. But here's the thing. They do reach the ground, in huge numbers. Detectors at sea level pick up muons from cosmic ray showers all the time. Right now, as you're lying there, something like 10,000 muons are passing through every square meter of the Earth's surface every minute. They're going through you right now, harmlessly, but they're there. And they shouldn't be. Not unless something is stretching their lifetimes. And that something is time dilation. Because those muons are moving at something like 99.9% of the speed of light. At that speed, the Lorentz factor, that gamma we talked about earlier, gets really big. Time for the muon, as seen from our perspective on the ground, is running much slower than our time. So while the muon experiences only its usual 2.2 microseconds of life, from our frame of reference, it lives much longer, long enough to traverse the entire atmosphere and reach our detectors. This was recognized as early as the late 1930s and early 1940s. In 1941, Bruno Rossi and David Hall did a beautiful experiment on Mount Washington in New Hampshire, comparing the number of muons detected at the top of the mountain, about 2,000 meters up, with the number detected at sea level. If muons were decaying at their normal rest frame rate, you'd expect far fewer at the bottom than they actually measured. But the numbers they got matched almost perfectly with what special relativity predicted. The muons were living longer because they were moving fast. Time dilation was real, and cosmic rays were proving it every second of every day. Now, what's lovely about this is that you can also flip the perspective, and it still works. From the muon's point of view, its internal clock is ticking normally. It still only lives for 2.2 microseconds. But from the muon's frame of reference, the atmosphere is rushing upward toward it at 99.9% of the speed of light. And because of length contraction, the other weird consequence of special relativity, the atmosphere appears compressed. That 15-kilometer column of air looks to the muon like it's only a few hundred meters thick. So the muon doesn't need extra time. The distance is shorter. Both perspectives give you the same answer. The muon reaches the ground. It's just that one explanation uses time dilation and the other uses length contraction. And they're two sides of the same relativistic coin. That muon result was compelling, but it was indirect. What people really wanted was to directly measure time dilation with actual clocks. And that brings us to one of the most famous experiments in 20th century physics, the Haefel-Keating experiment of 1971. Joseph Haefel was a physicist at Washington University in St. Louis, and Richard Keating was an astronomer at the United States Naval Observatory. Their idea was almost absurdly simple. Take extremely accurate clocks, cesium beam atomic clocks, the best available at the time, and fly them around the world on commercial airliners. Compare them to identical clocks that stayed on the ground. If Einstein was right, the flying clocks should come back showing a different time. Now, there were two effects to account for. Special relativity says the moving clocks should tick slower because of their velocity. That's the velocity-based time dilation. But general relativity says the flying clocks should tick faster because they're higher up, farther from Earth's gravitational center, in weaker gravity. That's the gravitational time dilation. The two effects work in opposite directions, and their relative sizes depend on the speed and altitude of the flight, and also on the direction, east or west, because the Earth is rotating, and that rotation matters for calculating the total velocity relative to the non-rotating frame. So Hafele and Keating actually did it. In October 1971, they loaded 4 cesium clocks into seats on commercial Pan Am and TWA flights. They literally bought the clocks their own plane tickets, and there are wonderful photos of these big, boxy atomic clocks strapped into passenger seats with seatbelts on. They flew eastward around the world, brought the clocks back, compared them to the reference clocks at the Naval Observatory, then did it again flying westward. The predictions were specific. For the eastward trip, the velocity effect and the gravitational effect partially cancel, but the velocity effect wins. The eastward flying clocks should lose about 40 nanoseconds. For the westward trip, the effects add together. The westward flying clocks should gain about 275 nanoseconds. And when they compared the clocks, the eastward clocks had lost 59 nanoseconds, and the westward clocks had gained 273 nanoseconds. Given the experimental uncertainties, which were significant, these were commercial flights with varying altitudes and speeds. The results agreed with Einstein's predictions within the margin of error. Think about what that means. In 1971, 2 guys took some clocks on airplanes, flew around the world, and proved that time itself runs at different rates depending on how fast you're moving and how deep you are in a gravitational field. The effect was tiny, billionths of a second, but it was real and it was measured. The universe actually works this way. Now, the Hafele-Keating experiment was groundbreaking, but it was also a bit rough around the edges. The uncertainties were large. The commercial flights introduced all sorts of variables, and some critics questioned whether the results were as clean as claimed. The real precision came later, with better technology. In 1976, the Gravity Probe A experiment took things to another level. Robert Vesso and Martin Levine at the Smithsonian Astrophysical Observatory launched a hydrogen maser clock, a type of atomic clock even more stable than cesium, on a suborbital rocket to an altitude of about 10,000 kilometers. They compared its frequency to an identical clock on the ground using a clever two-way radio link that canceled out the Doppler effect. The result confirmed gravitational time dilation to a precision of about 70 parts per million. Einstein's prediction nailed. And then the precision just kept getting better. By 2010, a group at the National Institute of Standards and Technology, NIST, in Boulder, Colorado, led by Chin-Wen Cho, demonstrated gravitational time dilation across a height difference of just 33 centimeters, 1/3 of a meter. They used aluminum-ion optical clocks, which are so precise they would neither gain nor lose a second in about 3.7 billion years. And they showed that the clock sitting 33 centimeters higher ticked faster by exactly the amount general relativity predicts. You could put one clock on a table and another on the floor, and the one on the table ages faster. Not by much, by a few parts in 10 to the 17th, but measurably, reproducibly. Really. That experiment changed how I think about this, because it takes time dilation out of the realm of exotic physics, black holes, neutron stars, spacecraft, and puts it right here, in a room, on a tabletop. The top of your head is aging faster than your feet, by an amount so small you could never perceive it, but the universe is keeping track. Every atom in your body is experiencing a slightly different flow of time, depending on its height in Earth's gravitational field. And if that doesn't quietly blow your mind while you're lying there, I don't know what will. But here's what really ties all of this together, and why the experimental thread matters so much. Every one of these measurements, the moons, the airplane clocks, the rocket macers, the tabletop optical clocks, they all agree with the same set of equations. The ones Einstein wrote down in 1905 and 1915. The framework hasn't needed patching or revision. It's held up across a staggering range of conditions, from billionths of a second on a commercial flight to the 20% time slowdown on a neutron star's surface. That's the mark of a truly deep theory. It doesn't just work in the laboratory where it was born. It works everywhere you take it. And that universality is exactly what made it possible to do something that might be the most dramatic experimental achievement in the history of physics. Something we touched on briefly when we talked about Kip Thorne's Nobel Prize. Because the same equations that predict time dilation also predict that accelerating masses should create ripples in the fabric of space-time itself, gravitational waves. And detecting those waves required building the most sensitive measuring instrument ever constructed by human beings, an instrument so precise that it can detect a change in length smaller than 1/10,000th the diameter of a proton. And the story of how that instrument came to exist, the decades of doubt, the engineering nightmares, the personalities involved, the near cancellations, and the moment in September 2015 when a signal arrived that had been traveling for over 1 billion years. That story is one of the most human stories in all of science, because gravitational waves were predicted in 1916, just months after general relativity was published, and they weren't directly detected until 2015. That's 99 years. An entire century of people arguing about whether these waves were even real, whether they carried energy, whether they could ever be measured, and whether it was worth spending billions of dollars trying. And the fact that we got there at all is honestly kind of a miracle. So let's slow down and really live inside this one for a while, because it deserves the space. Einstein himself went back and forth on gravitational waves. He predicted them in 1916. Then in 1936, he wrote a paper with Nathan Rosen claiming they didn't exist, that the solutions contained singularities that made them unphysical. He submitted it to the Physical Review, and the anonymous referees sent back a detailed report pointing out errors in the argument. Einstein was furious. He'd never had a paper refereed before. In European journals at the time, editors just accepted or rejected. And he fired off an angry letter saying he hadn't authorized anyone to show the paper to a third party. He withdrew it and sent it to a different journal. But here's the twist. His assistant, Leopold Infeld, working through the math independently, realized the referee had actually been right. The singularities Einstein and Rosen found were coordinate artifacts. They were like the way longitude lines converge at the poles on a map, a feature of the coordinate system, not a real physical problem. Einstein quietly revised the paper before it appeared in the Journal of the Franklin Institute, and the published version actually proved that gravitational waves do exist. The anonymous referee, by the way, was almost certainly Howard Percy Robertson, a Princeton physicist. He saved Einstein from publishing an incorrect result, and Einstein never thanked him, never even knew who he was. So even the man who invented general relativity nearly convinced himself that one of its most important predictions was wrong. That gives you a sense of how subtle this stuff is. For decades after that, the theoretical status of gravitational waves remained murky. There was a famous debate at a 1957 conference in Chapel Hill, North Carolina, where a young physicist named Richard Feynman, yes, that Feynman, presented what's now called the sticky bead argument. Imagine a rod with two beads on it, free to slide. If a gravitational wave passes through, it will alternately stretch and compress space in perpendicular directions. The beads would slide back and forth on the rod, and friction would generate heat. Heat is energy. If the wave can deposit energy into a physical system, then the wave must be carrying energy, and therefore it must be physically real. It's such a clean argument. So elegant, and it essentially settled the theoretical debate. Gravitational waves are real, they carry energy, and in principle, they're detectable. In principle. Because here's the engineering problem, and it's a monster. The waves that reach Earth from astrophysical sources are unimaginably faint. When two black holes spiral into each other 1 billion light-years away, the gravitational waves they produce are powerful beyond comprehension at the source. They briefly radiate more energy than all the stars in the observable universe combined. But by the time those waves reach us, they've spread out over such an enormous volume of space that the distortion they produce is almost laughably small. We're talking about a change in the length of a 4-kilometer-long detector arm by about 1/10,000th the diameter of a proton. That's roughly 10 to the minus 19 meters. To put that in perspective, if you scaled the detector arm up to the distance from Earth to the nearest star, the change you'd need to measure would be about the width of a human hair. That's the level of precision we're talking about. The first person to seriously attempt detection was Joseph Weber, a physicist at the University of Maryland. In the 1960s, Weber built what are called resonant bar detectors, large aluminum cylinders about 2 meters long and 1 meter in diameter, weighing over a ton. The idea was that a passing gravitational wave would make the bar ring like a bell, vibrating at its resonant frequency, and you could pick up that vibration with piezoelectric sensors. Weber claimed in 1969 that he had detected gravitational waves. He said he was seeing coincident signals in 2 detectors separated by 1,000 kilometers, which would rule out local noise. The physics community was electrified. This would have been one of the greatest experimental achievements ever. But then other groups built their own bars, and nobody could reproduce his results. The signals Weber reported were far stronger than any theoretical source could explain. Over the following years, it became clear that Weber's detections were almost certainly spurious, probably the result of subtle errors in his data analysis. It was a painful episode. Weber never accepted that his detections were wrong. He continued to defend them until his death in 2000, increasingly isolated from the mainstream community. And the whole affair left a cloud of skepticism over the entire field of gravitational wave detection. Funding agencies were wary. Physicists were wary. The idea of actually detecting these waves seemed, to many serious people, like a fool's errand. And this is where the story gets really interesting, because into that skeptical environment walked a handful of people who were stubborn enough, or visionary enough, to push forward anyway. The 3 names you need to know are Rainer Weiss, Kip Thorne, and Ronald Drever. Weiss was an experimentalist at MIT. Thorne was a theorist at Caltech. We've already met him in connection with black holes and interstellar. Drever was a brilliant, difficult Scottish experimentalist who also ended up at Caltech. Together, and often in conflict with each other, they laid the groundwork for LIGO, the Laser Interferometer Gravitational-Wave Observatory. The basic concept goes back to an idea Weiss sketched out in remarkable detail in a 1972 MIT technical report. Instead of a resonant bar, you use laser interferometry. You split a laser beam, send the two halves down two perpendicular arms, bounce them off mirrors at the far ends, and recombine them. If the arms are exactly the same length, the light waves recombine in a specific way. They interfere destructively, and you see darkness at the output. But if a gravitational wave passes through and stretches one arm while compressing the other, even by a tiny fraction of the wavelength of light, the interference pattern shifts, and you see a signal. The longer the arms, the bigger the absolute length change for a given wave amplitude, so you want the arms as long as possible. Weiss's 1972 report didn't just describe the concept. It systematically cataloged every source of noise that could mimic or obscure a signal: seismic vibrations, thermal noise in the mirrors, fluctuations in the laser light, residual gas molecules in the beam tubes, and estimated how each one could be controlled. It was essentially a blueprint for LIGO, written 23 years before construction began. And it was staggeringly ambitious. Weiss was proposing to measure distances with a precision that most physicists considered flatly impossible. The road from that 1972 report to a working detector was brutal. Drever and Weiss clashed constantly over technical approaches. Drever was a genius in the lab, but nearly impossible to work with in a large collaboration. The project went through multiple directors. There were internal politics, external funding battles, and a genuine question about whether the National Science Foundation should spend what would eventually amount to over $1 billion on an instrument that might never detect anything. The NSF's investment in LIGO became the largest single investment it had ever made in a physics experiment. Think about that pressure. If it didn't work, it wouldn't just be a scientific failure. It would be a political one. Ammunition for everyone who thought big science was a waste of money. The person who ultimately made LIGO work as a project, who turned it from a collection of brilliant but fractious physicists into a functioning, managed, deliverable instrument, was Barry Barish, a Caltech particle physicist, who took over as director in 1994. Barish brought the organizational discipline of big particle physics experiments. He restructured the collaboration, established clear milestones, and crucially, he championed the plan for advanced LIGO, an upgraded version of the detector that would be roughly 10 times more sensitive than the initial configuration. That factor of 10 matters enormously because making a detector 10 times more sensitive means you can survey a volume of space 1,000 times larger, which means you're 1,000 times more likely to catch an event. The initial LIGO detectors ran from 2002 to 2010 and detected nothing, which was actually consistent with theoretical predictions. They probably weren't quite sensitive enough. Then the detectors were shut down for a 5-year upgrade to the advanced LIGO configuration. New mirrors, new suspensions, new laser systems, new seismic isolation. Every component pushed to the edge of what physics and engineering could deliver. The mirrors alone are extraordinary. 40-kilogram cylinders of ultra-pure fused silica, polished to a smoothness of about 1 nanometer, suspended on fused silica fibers thinner than a human hair to minimize thermal noise. The vacuum system enclosing the laser beams is one of the largest high-vacuum systems in the world, over 10,000 cubic meters pumped down to a trillionth of an atmosphere. And here's where the universe delivered one of the great dramatic moments in the history of science. Advanced LIGO hadn't even officially started its first observing run. The detectors were in an engineering shakedown phase, being tested and calibrated. On September 14th, 2015, at 5:51 in the morning Eastern Time, A signal swept through the detector in Livingston, Louisiana, and then, 7 milliseconds later, through the detector in Hanford, Washington, 3,000 kilometers away. The signal lasted about 0.2 of a second. It was a characteristic chirp, a rising frequency and amplitude, exactly matching what general relativity predicted for two black holes spiraling into each other and merging. The black holes were about 36 and 29 solar masses, orbiting each other at nearly the speed of light in their final moments, and the merger produced a single black hole of about 62 solar masses. If you do the arithmetic, you'll notice that 36 plus 29 is 65, not 62. Those three missing solar masses, 3 times the mass of our Sun, were radiated away as gravitational wave energy in a fraction of a second. 3 suns worth of mass, converted entirely into ripples in space-time. The peak power output, for that brief instant, was about 50 times greater than the combined light output of every star in the observable universe. The signal had traveled 1.3 billion light-years to reach us. It was generated when multicellular life on Earth was just beginning to figure out sexual reproduction. And it arrived at a moment when the detectors happened to be turned on, in a configuration sensitive enough to catch it, staffed by people who had spent decades preparing for exactly this. The team spent months verifying the signal, ruling out every conceivable source of error before announcing it publicly on February 11, 2016. Weiss, Barish, and Thorne shared the 2017 Nobel Prize in Physics. Drever, tragically, had developed dementia and was in a nursing home by the time of the detection. He died in 2017, and the Nobel is not awarded posthumously. Over 1,000 scientists contributed to the result. Now, you might be wondering, we've been talking about time dilation for a while now, and gravitational waves sound like a different topic. But here's the thing, and this is really the deep connection that makes the whole story cohere. Gravitational waves are time dilation. Or more precisely, they're oscillating distortions of space-time, and time dilation is a static distortion of space-time. They're the same phenomenon in different modes, the way a still pool of water and a wave on that pool are both manifestations of the same medium. When a gravitational wave passes through LIGO, it's not just stretching and compressing space, it's also subtly altering the flow of time along each arm. The laser interferometer works because light is the ultimate clock, and the wave is disrupting that clock differently in the two arms. Every concept we've been building up, the equivalence principle, the curvature of space-time near massive objects, the slowing of clocks in gravitational fields, all of it is encoded in the same mathematical framework that predicts gravitational waves. Detecting those waves was the ultimate confirmation that space-time really is a dynamic, flexible fabric, exactly as Einstein described. And LIGO wasn't done after that first detection. In August 2017, both LIGO detectors and the Virgo detector in Italy picked up a signal that was different from the black hole mergers they'd been seeing. This one lasted much longer, about 100 seconds, and the frequency was lower. It was 2 neutron stars spiraling together, each about 1.4 solar masses, in a galaxy called NGC 4993, about 130 million light-years away. And here's what made this one extraordinary. Because neutron stars aren't black holes. They don't just swallow everything when they collide. They explode. They produce light. And that meant, for the first time ever, astronomers could point their telescopes at the same event that the gravitational wave detectors were feeling. Within seconds of the gravitational wave signal, NASA's Fermi satellite detected a short gamma-ray burst from the same patch of sky. Within hours, telescopes around the world were swinging toward NGC 4993, And they found it, a new point of light in that galaxy, a kilonova, the aftermath of two neutron stars smashing together at a significant fraction of the speed of light. This was the beginning of what scientists call multi-messenger astronomy, and it's one of those moments where you realize the world has genuinely changed. Before August 2017, we could listen to the universe through gravitational waves, or we could look at it through light, but we'd never done both at once for the same event. Now we could. And the physics that poured out of that single observation was staggering. That kilonova, that glowing debris cloud, turned out to be a factory for heavy elements. Gold, platinum, uranium, the stuff that's too heavy to be forged in ordinary stars. For decades, physicists had debated where those elements come from. Supernovae were the leading candidate, but the numbers never quite worked out. This one neutron star merger produced something like 10 Earth masses of gold. 10 Earth masses, just scattered into space, cooling, eventually mixing into gas clouds that would someday form new stars and planets. The gold in your jewelry, the platinum in catalytic converters, the uranium in nuclear reactors. There's a real chance much of it was forged in events exactly like this one, billions of years ago, before our solar system even existed. But let's come back to time dilation, because even in this spectacular collision, it's there, woven through everything. Those two neutron stars, in the final seconds before they merged, were orbiting each other hundreds of times per second. Hundreds of times per second. Think about what that means for their velocity. They were moving at something like 20 or 30% the speed of light. At those speeds, special relativistic time dilation is significant. Clocks on those neutron star surfaces, if you could somehow place clocks there, would be running noticeably slower than clocks far away. And on top of that, each neutron star has a gravitational field so intense that time on its surface already runs about 20 to 30% slower than time in flat space. So you've got both flavors of time dilation, gravitational and velocity-based, stacked on top of each other, in the most extreme way nature can manage, right there in the signal that LIGO and Virgo recorded. And the beautiful thing is that the waveform, the shape of the gravitational wave signal, encodes all of that. The way the frequency chirps upward, the way the amplitude grows, the precise moment it cuts off, all of it is determined by general relativity, by the curvature of space-time around those spiraling objects. When physicists match their theoretical templates to the observed signal, they're essentially solving Einstein's field equations for that specific configuration of matter and energy, and extracting the masses, the spins, the distance, the orientation. It's general relativity being used as a precision measurement tool over 100 years after it was written down. Einstein would have been astonished, or maybe not. Maybe he would have just nodded and said, "Yes, well, the theory is correct. What did you expect?" So, let's take a step back and think about where we are in this story. We started with Maxwell's equations and a young patent clerk who couldn't stop thinking about what it would be like to ride alongside a beam of light. We followed that thread through the equivalence principle, through the decade-long struggle to build general relativity, through the experimental confirmations, muons, airplane clocks, rocket clocks, optical clocks on tabletops. We watched the gravitational wave story unfold over a full century, from Einstein's tentative 1916 prediction to the triumphant 2015 detection. And through all of it, the central idea has been the same. Time is not fixed. Time is not a backdrop. Time is part of the physical world, and it responds to mass, energy, and motion. Now here's where I want to spend some time, because there's an aspect of time dilation that we haven't really explored yet, and it's the one that tends to keep people up at night, which I realize is the opposite of what we're going for here. But bear with me, because I think it's actually deeply calming once you sit with it. And that's the question of whether time dilation is real. Not in the experimental sense. We've covered that, and the answer is unambiguously yes. The clocks really do disagree. The muons really do live longer. GPS really does need those corrections. But in the philosophical sense, what does it mean for time to pass at different rates in different places? Is your time more real than the time on a neutron star? Is there a true time somewhere? This question actually has a long and fascinating history in physics, and it connects to something called the block universe, which is one of the stranger ideas to come out of relativity. Here's the setup. In Newtonian physics, there's a universal clock. Everyone agrees on what time it is, everywhere, always. The universe has a single, shared now. This moment, right now, is the same moment everywhere. Past, present, future, they're absolute categories. The past is gone, the future hasn't happened yet, and the present is the thin knife edge between them. But special relativity breaks that, and it breaks it in a very specific way. Remember the key insight. The speed of light is the same for all observers, regardless of their motion. One of the consequences of that, which Einstein worked out in 1905, and which his former professor Hermann Minkowski reformulated beautifully in 1908, is that simultaneity is relative. Two events that happen at the same time according to one observer do not necessarily happen at the same time according to another observer, moving at a different velocity. This isn't a trick of perception or measurement delay, it's fundamental. There is no fact of the matter about whether two spatially separated events are simultaneous. It depends on your state of motion. Minkowski, by the way, is a wonderful character in this story. He had been Einstein's mathematics professor at the ETH in Zurich, and he hadn't been particularly impressed with the young Einstein as a student. He later called him a lazy dog. But when Einstein published Special Relativity, Minkowski recognized something profound in it. And in 1908, he gave a famous lecture in which he said, "Henceforth space by itself, and time by itself, are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. That union is space-time." Minkowski showed that special relativity is most naturally understood not as a theory about space and time separately, but as a theory about a four-dimensional space-time continuum, where time is just another dimension, woven together with the three spatial dimensions into a single geometric structure. And here's where the block universe idea comes in. If simultaneity is relative, if there's no universal now, then it becomes very hard to maintain the idea that the past is gone and the future doesn't exist yet. Think about it this way. Suppose you and I are sitting in the same room, at rest relative to each other. We agree on what's happening now on some distant star. But if I start moving toward that star, even very slowly, my now slice through space-time tilts. Events that were in the future for you are now in my present. Events that were in your present are now in my past. For everyday speeds and everyday distances, this effect is negligible, fractions of a nanosecond. But for large distances, like across the galaxy, even walking speed can shift your now by thousands of years. So if my now includes events that are in your future, and your now includes events that are in my past, then what does it even mean to say that only the present is real? Some physicists and philosophers take this argument seriously and conclude that all of space-time, past, present, and future, exists equally. The universe isn't something that unfolds moment by moment. It's a four-dimensional block, and our experience of time flowing is something like the experience of moving through a landscape that was always there. This is the block universe, and it's a legitimate interpretation of the physics. Now, I should say, not everyone agrees with this. There are physicists who argue that the block universe reading goes too far, that there are ways to preserve a meaningful notion of becoming, even within relativity. The debate is genuinely unresolved, and it touches on some of the deepest questions in philosophy. Questions about consciousness, free will, the nature of experience. But what I find calming about it, and here's why I think it's actually a good thing to think about as you're drifting off, is that it suggests a kind of cosmic patience. If the block universe is right, then nothing is truly lost. Every moment you've ever experienced is still there, in some sense, embedded in the geometry of space-time. The afternoon you spent as a child watching clouds, the conversation you had last week, they're not gone. They're just elsewhere in the block. Whether or not you find that comforting probably depends on your temperament. But it's worth noting that this isn't mysticism. It's a straightforward reading of the same equations that make GPS work and that predicted gravitational waves a century before we detected them. The mathematics doesn't care whether we find its implications cozy or unsettling. It just is. And this connects to something else that's been quietly running through our whole story, something about the nature of scientific theories and what it means for a theory to be true. Because Einstein's general relativity is, by any reasonable measure, one of the most successful theories in the history of science. Every prediction it's made has been confirmed. Every test it's been subjected to, it has passed. And yet physicists are almost certain it's not the final word. There's something deeper underneath it, something that reconciles gravity with quantum mechanics, and we don't know what it is yet. The search for that deeper theory, quantum gravity, is one of the great open problems in physics, and time dilation sits right at the heart of it. Because in quantum mechanics, time plays a very different role than it does in general relativity. In quantum mechanics, time is a background parameter. It ticks along uniformly, providing a stage for quantum events to unfold on. In general relativity, time is dynamic, flexible, part of the show. Merging these two pictures requires understanding what time fundamentally is at the deepest level, and nobody has figured that out yet. There are candidates, of course. String theory is one. Loop quantum gravity is another. In loop quantum gravity, space-time itself is quantized. It comes in discrete chunks, like pixels, at an unimaginably tiny scale called the Planck length, about 10 to the minus 35 meters. At that scale, the smooth fabric of space-time that Einstein described would dissolve into something granular, something foamy, and the very concept of time dilation might need to be reformulated. Some loop quantum gravity models suggest that time near a singularity, say, at the center of a black hole, doesn't actually stop, the way classical general relativity predicts. Instead, the quantum structure of space-time prevents the singularity from forming at all, and what looks like a black hole from the outside might actually be a tunnel, a bounce, a transition to something else entirely. And this is where things get genuinely speculative, which is a nice place to be when you're lying in the dark, because speculation is just imagination with equations behind it. One of the most intriguing ideas to come out of quantum gravity research in recent years involves something called the holographic principle. And it starts with a puzzle that the physicist Jacob Bekenstein noticed in the early 1970s, a puzzle about black holes and information. Specifically, how much information a black hole can contain. See, in ordinary physics, if you have a room, the amount of information you can cram into that room scales with its volume. Double the size of the room, you can fit roughly 8 times as much stuff in there, 8 times as much information. That seems obvious, right? Bigger space, more room for things. But Bekenstein realized that black holes don't work that way. When he studied the thermodynamics of black holes, and the fact that black holes even have thermodynamics is itself a wild story, he found that the maximum amount of information a black hole can hold doesn't scale with its volume. It scales with its surface area, the area of the event horizon. That's bizarre. It's as if all the information about everything that ever fell into the black hole, every star, every planet, every unlucky astronaut, is somehow encoded on the 2-dimensional surface of the event horizon, like a hologram. You know how a hologram works, right? A flat, 2-dimensional piece of film that encodes a fully 3-dimensional image. You look at it from different angles, and you see depth, you see structure, but all that information is actually stored on a flat surface. Bekenstein was suggesting something similar might be true for black holes, and by extension, possibly for the entire universe. Stephen Hawking initially pushed back on some of Bekenstein's ideas, but in the process of trying to prove Bekenstein wrong, Hawking actually discovered something even more remarkable: that black holes radiate. They emit particles. They have a temperature. This is Hawking radiation from 1974, and it's one of the most beautiful results in theoretical physics because it ties together general relativity, quantum mechanics, and thermodynamics in a single equation. Hawking showed that the temperature of a black hole is inversely proportional to its mass. Small black holes are hot, large ones are cold, and this means black holes can evaporate. Given enough time, a black hole will radiate away all its energy and disappear entirely. For a stellar mass black hole, this would take something like 10 to the 67 years, which is so much longer than the current age of the universe that it's practically forever. But in principle, it happens. Now, here's where time dilation weaves back into this. Think about what Hawking radiation looks like from different perspectives. If you're far away from the black hole, watching from a safe distance, you see the black hole slowly radiating, slowly shrinking, slowly evaporating over those incomprehensible timescales. But if you're falling into the black hole, your experience of time is so dramatically dilated relative to the distant observer that you might cross the event horizon without noticing anything special at all. No wall of fire, no dramatic boundary, just a smooth passage into the interior. Meanwhile, from the outside observer's perspective, you never actually cross. You appear to freeze at the horizon, your image reddening and dimming as the photons reaching the distant observer get stretched to longer and longer wavelengths by the gravitational time dilation. Two completely different stories about the same event, both equally valid within their own frames. And the puzzle of reconciling these two stories, what the infalling observer experiences versus what the distant observer sees, is one of the deepest, unsolved problems in physics. It's called the black hole information paradox, and it's been driving theoretical physicists slightly crazy for about 50 years now. The holographic principle grew out of this tangle. In 1993, the Dutch Nobel laureate Gerard 't Hooft proposed that the Bekenstein bound, that information scales with area result, might not be special to black holes. It might be a fundamental property of any region of space. Any volume of space, 't Hooft suggested, can be fully described by information encoded on its boundary. 3 years later, Leonard Susskind formalized this into what we now call the holographic principle. And in 1997, Juan Maldacena, a young Argentine-American physicist working at Harvard, provided the most concrete realization of it. A mathematical correspondence between a theory of gravity in a particular kind of curved spacetime and a quantum field theory living on the boundary of that spacetime, with one fewer spatial dimension. It's called the ADS/CFT correspondence, and it's one of the most influential results in theoretical physics in the last 30 years, even though it technically applies to a kind of spacetime, anti-de Sitter space, that isn't quite like our own universe. But here's what matters for our story about time. If the holographic principle is correct in some form, then the time dilation you experience in a gravitational field, the stretching and warping of time that Einstein described, might be, at the deepest level, a consequence of how information is organized on a lower dimensional boundary. Time dilation wouldn't just be a feature of curved spacetime. It would be a feature of how the hologram works. The bending of time would emerge from something more fundamental, something that doesn't itself contain time in the way we understand it. That's a staggering thought. It means time, as we experience it, the ticking of clocks, the aging of cells, the drift towards sleep, might be emergent, not fundamental, not woven into the deepest layer of reality, but arising from it, the way temperature arises from the motion of molecules. No individual molecule has a temperature. Temperature is what you get when you zoom out and look at the collective behavior. Time might be like that. Time dilation might be like that. And this connects to something even more recent, something that's been generating enormous excitement in theoretical physics over the last decade or so. It turns out that the mathematics of quantum entanglement, that spooky correlation between distant particles that Einstein himself found so troubling, might be intimately connected to the structure of spacetime itself. In 2013, Maldacena and Susskind proposed a conjecture with the wonderfully compact name ER equals EPR. ER refers to Einstein-Rosen bridges, wormholes, which Einstein and Nathan Rosen described in 1935. EPR refers to the Einstein-Podolsky-Rosen paradox, also from 1935, which first highlighted the strangeness of quantum entanglement. Maldacena and Susskind suggested that these two things, which seem completely unrelated, are actually the same thing seen from different angles. Every pair of entangled particles, they proposed, is connected by a tiny microscopic wormhole. Space-time geometry, in other words, might be stitched together by quantum entanglement. If that's true, and it's still very much a conjecture, not a proven result, then the curvature of space-time that causes time dilation is ultimately a manifestation of patterns of entanglement in some underlying quantum system. The reason your clock runs slower near a massive object would trace back, at the very bottom, to how quantum information is entangled in the fundamental degrees of freedom of the universe. That's so far from where we started, isn't it? We started with Maxwell's equations, with Michelson and Morley's interferometer in a basement in Cleveland, with Einstein on a streetcar in Bern, imagining what it would be like to ride alongside a beam of light. And now we're here, at the frontier, where time dilation connects to holography, to entanglement, to the very question of whether space-time is fundamental or emergent. The thread runs all the way through. And yet, and this is the part I find most beautiful, the practical reality of time dilation hasn't waited for these deep questions to be resolved. While theorists debate whether space-time is woven from entanglement, engineers are building systems that depend on time dilation corrections with exquisite precision. The GPS satellites we talked about earlier are just the beginning. The European Galileo navigation system, the Chinese Beidou system, the Russian GLONASS system, all of them incorporate relativistic corrections. Every time you open a mapping app on your phone, you're relying on both special and general relativistic time dilation being accounted for, down to the nanosecond. And the next generation of navigation systems will need to be even more precise because the applications keep getting more demanding. Autonomous vehicles, precision agriculture, drone delivery, synchronized power grids. As clock technology improves, as we move from cesium clocks to optical lattice clocks that are accurate to 1 part in 10 to the 18th, the relativistic corrections become not just important, but dominant. At that level of precision, you can't ignore time dilation from a height difference of a single centimeter. The very shape of Earth's gravitational field becomes visible in the ticking of clocks, and people are now seriously proposing to use networks of ultra-precise clocks as a new way to map Earth's gravitational field, a technique called relativistic geodesy, or sometimes chronometric leveling. You'd measure the shape of the planet not with satellites or surveying equipment, but with clocks. Clocks that run at slightly different rates because they sit at slightly different heights in Earth's gravitational potential. Einstein would have loved that. The theory he built from pure thought experiments, from imagining elevators and light beams and trains, turned into a tool for measuring the literal shape of the world. And it goes further than Earth. As we push deeper into the solar system, time dilation becomes a practical navigation concern for spacecraft. The Juno probe orbiting Jupiter experiences measurably different time dilation than a probe in deep space, because Jupiter's gravitational field is so much stronger than what we're used to. Future missions to the outer planets, to the moons of Saturn, will need increasingly sophisticated relativistic corrections. And if we ever send humans to these places, which is still a long way off, but not impossible, the crew will age at a slightly different rate than people back on Earth. Not by much, not in any way they'd notice, but measurably. The clocks on the ship and the clocks on Earth will disagree, and the disagreement will be real. Not an illusion, not a trick of measurement. A genuine physical difference in the passage of time. And that brings us to something that I think is worth sitting with for a moment because it connects the cutting edge of physics to something deeply personal. Time dilation tells us that time is not what we intuitively think it is. It's not a river flowing at a constant rate. It's not a universal metronome keeping the cosmos in sync. It's local. It's personal. Your time depends on where you are and how you're moving. And at the deepest level, it might not even be fundamental. It might emerge from something we don't yet fully understand, something involving information and entanglement and the holographic structure of reality. But here's what I keep coming back to. Even though our understanding of time has been revolutionized again and again, by Einstein in 1905, by Minkowski in 1908, by the experimentalists with their muons and atomic clocks and laser interferometers, by the theorists with their black holes and holograms, even after all of that, time still feels the same. You're lying there, and the seconds are passing, and each one feels like a second. Your experience of time hasn't changed. What's changed is your understanding of what that experience means, and how it connects to the structure of the universe around you. And there's something profoundly comforting in that, I think. The universe is stranger than we imagined, but we're still here, still experiencing it, still finding our way through it, one moment at a time. And maybe that's the most remarkable thing of all. Not that time bends, not that clocks disagree, not that the geometry of space-time warps around mass and energy, but that a species of curious primates on a small rocky planet figured all of this out. Figured it out with thought experiments on trains, with mirrors and light beams, with chalk on blackboards and pencil on paper. Figured it out and then proved it again and again with increasingly beautiful experiments, each one confirming that the universe really does work this way, no matter how strange it seems. Think about the arc of that story for a moment. In 1905, a patent clerk in Bern realizes that the speed of light is the same for everyone, and from that single, stubborn fact, he deduces that time itself must be flexible. 10 years later, he extends that insight to gravity, showing that mass and energy curve the fabric of spacetime, and that what we call gravity is really the geometry of that curvature. A few years after that, Minkowski's mathematical framework gives us the language to talk about spacetime as a single unified thing, and Schwarzschild, working from the trenches of the First World War, finds the first exact solution to Einstein's field equations and inadvertently predicts black holes. Then decades pass. Oppenheimer and Snyder show that stars really can collapse into these things. Wheeler gives them a name. Experimentalists start measuring time dilation with muons raining down from the upper atmosphere, with atomic clocks flown around the world on commercial airliners, with hydrogen masers launched on rockets. Each experiment says the same thing. Einstein was right. Time really does run differently depending on where you are and how fast you're moving. And then the technology catches up to the theory. GPS satellites start orbiting the Earth, and the engineers building the system realize they have to account for both special and general relativistic effects, or the whole thing falls apart. 38 microseconds a day. That's what the clocks on those satellites gain relative to clocks on the ground. And if you don't correct for it, your position drifts by kilometers. Relativity isn't abstract anymore. It's in your phone. It's guiding your car to the nearest gas station. It's helping planes land in fog. Every time you open a map app and see that little blue dot showing exactly where you are, you're relying on corrections that Einstein's theory demands. That's extraordinary when you stop and think about it. And the story keeps going. Gravitational-wave detectors, LIGO, Virgo, start listening to the universe in an entirely new way, picking up the ripples in space-time caused by colliding black holes and merging neutron stars. Those ripples are time dilation in motion, stretching and compressing the fabric of space and time as they pass through. The 2017 neutron star merger gives us gravitational waves and electromagnetic radiation arriving from the same event, confirming that gravitational waves travel at the speed of light, just as Einstein predicted a century earlier. And optical lattice clocks become so precise that they can detect the difference in the flow of time across a height difference of a single centimeter. A centimeter. That's less than the width of your finger. And yet time runs measurably faster at the top of that centimeter than at the bottom, because the top is ever so slightly farther from the center of the Earth, ever so slightly less deep in Earth's gravitational well. These clocks aren't just scientific curiosities. They're opening up entirely new ways of understanding our planet. Relativistic geodesy, using the rate of time to map the gravitational field of the Earth, could revolutionize how we monitor sea level rise, how we detect underground reservoirs of magma or water, how we track the slow movements of tectonic plates, the shape of the Earth, its interior structure, its changing mass distribution as ice caps melt and oceans shift. All of this is encoded in the subtle variations of how fast time passes from place to place, and we're just beginning to read that code. Meanwhile, the theorists are pushing deeper. the tension between general relativity and quantum mechanics, the two greatest theories in physics, both spectacularly successful in their own domains, both apparently incompatible at the deepest level, remains one of the great unsolved problems in science. String theory offers one possible path to reconciliation, loop quantum gravity offers another, and the holographic principle suggests that the three-dimensional reality we experience might be a projection of information encoded on a two-dimensional boundary. If that's true, and the mathematics of ADS/CFT correspondence strongly suggests something like it is, then time dilation might not be a fundamental feature of reality at all. It might be emergent. It might arise from the way information is organized at a deeper level, a level we don't yet have the tools or the concepts to fully grasp. And that idea, that time itself might be emergent, is one of the most profound and unsettling ideas in all of physics. Because time feels so fundamental. It feels like the most basic thing there is. Before anything can happen, time has to pass. Right? That's how we think about it. But physics keeps hinting that this intuition might be wrong, that time might be something that emerges from a more fundamental, timeless structure, the way temperature emerges from the random motions of molecules. A single molecule doesn't have a temperature. Temperature is a collective property, a statistical property, something that only makes sense when you zoom out and look at billions of particles at once. Maybe time is like that. Maybe it only makes sense at our scale, in our experience, and at some deeper level. There's something else going on entirely. But here's the thing, and this is where I want to land, because I think it matters. Even if time is emergent, even if it arises from quantum entanglement or holographic information or some mathematical structure we haven't even imagined yet, your experience of it is real. The seconds passing as you lie there, the gentle weight of the day settling behind you, the slow drift toward sleep. That's real. It's as real as anything in physics. The fact that we can describe time with equations, that we can measure its variations with astonishing precision, that we can trace its behavior from the surface of a neutron star to the event horizon of a black hole to the interior of a GPS satellite. None of that diminishes the reality of your experience. If anything, it deepens it. It means that your quiet, personal experience of time passing is connected to the deepest structure of the universe. The same physics that governs black holes governs the clock on your nightstand. The same equations that predict gravitational waves predict the tiny difference in aging between your head and your feet. You are part of this story, not an observer looking in from the outside, but a participant, embedded in the same space-time geometry that Einstein spent a decade learning to describe. And the people who figured all of this out, they were just people. Einstein was a young man who couldn't get an academic job, so he worked at a patent office and thought about physics in his spare time. Minkowski was his former math teacher, a man Einstein had once dismissed as a pedant, who turned out to see something Einstein had missed. Schwarzschild was a soldier, doing mathematics in impossible conditions, driven by pure curiosity even as the world burned around him. Rossi and Hall were experimentalists who climbed a mountain in Colorado with Geiger counters to count muons. Haffel and Keating scraped together funding to buy extra seats on commercial flights for their atomic clocks. Pound and Rebka climbed the tower of the Jefferson Physical Laboratory at Harvard and bounced gamma rays between the basement and the top floor. Joe Weber spent decades building gravitational-wave detectors that never quite worked and was dismissed by much of the physics community. But his vision was eventually vindicated by LIGO, even if he didn't live to see the final triumph. Jocelyn Bell Burnell, a graduate student, noticed a bit of scruff on a chart recording and discovered pulsars, rotating neutron stars, where time dilation is dramatic and real. Kip Thorne spent 50 years championing the search for gravitational waves and lived to hear the chirp of two black holes merging 1 billion light-years away. These are human stories. Stories of stubbornness and brilliance and luck and failure and persistence. And they all circle around this one strange, beautiful, counterintuitive fact. Time is not what we thought it was. It bends, it stretches, it flows at different rates in different places. And somehow, despite all of that, it carries us forward, moment by moment, in a way that feels utterly natural and utterly constant, even though it isn't. So as you lie there, settling deeper into wherever you are, let that thought be a gentle one. The universe is strange, but it's comprehensible. It yields its secrets to patience and curiosity and careful thought. And the strangest thing about it, the thing that still amazes me every time I think about it, is that the strangeness doesn't make it less beautiful. It makes it more. The fact that time runs slower near a massive object isn't a flaw in the universe. It's a feature. It's how gravity works. It's how space-time curves. It's how the cosmos holds itself together. And you're part of it. Right now, lying still, gravity gently pulling you into your bed. Time flowing for you at your own particular rate. A rate that's yours alone, determined by your exact position in the gravitational field of the Earth, your exact velocity relative to the stars, the precise geometry of the space-time you're moving through. No one else in the universe has exactly your flow of time. Not quite. Not precisely. It's yours, and it will carry you, as it always has, gently and steadily, into whatever comes next. The equations describe it. The experiments confirm it. The clocks measure it. But you just live it. And that's enough. That's more than enough. So let the seconds pass. Let them be as long or as short as they want to be. Let Einstein and Minkowski and Schwarzschild and all the rest of them keep watch over the mathematics. You don't need to hold any of it in your mind. It's all still true whether you're thinking about it or not. The universe doesn't need your attention to keep running. It just runs. And time, your time, this particular thread of time that belongs to you, it just flows, gently, quietly, at exactly the rate it should, given where you are and how you're moving through this vast, curved, beautiful space-time that we're all part of. Let it carry you. You're in good hands. The physics works. It's been checked. And right now, the only thing it asks of you is to rest.